Okay, in this video we're going to be looking at mass energy equivalence and some simple calculations involving Einstein's famous equation, E is equal to mc squared. Now just a quick note, this video is being made for my physical science class, which is a class for non-science majors, and so I'm not going to show the dimensional analysis for the units like I would in most of my other classes. Okay, so in this problem we're told that the combustion or the burning of propane releases a relatively large amount of energy, at least for chemical reactions. And as an example, the burning of all the propane in a typical propane tank, like you would get from the grocery store, would result in the release of about 4.2 times 10 to the 5th kilojoules of energy. And so they want to know how much mass would be lost in this chemical reaction. All right, so fundamentally all they're asking us to do is they've given us the energy and they want us to calculate the mass. And then c is the speed of light that we've used before, and we'll be given that value. All right, the only thing we have to be careful of is the units. So the units on the energy need to be in joules, and the units on the mass need to be in kilograms. So I can't just plug this into the equation for E, I've got to convert the kilojoules into joules. So if you remember, the conversion factor is 1 kilojoule. It's 10 to the 3rd joules. So I'll take my 4.2 times 10 to the 5th kilojoules, then 1 kilojoule, 10 to the 3rd joules on top, so my units cancel, and this comes out to be 4.2 times 10 to the 8th joules. So now this is what I can plug in to E. So when I do that, so I've plugged in my E, now I'll put in my speed of light. Don't forget to square it. All right, so the number of ways that we could solve this problem. What I'm going to do is I'm going to evaluate this first. So I'm going to go ahead and square the speed of light. So then this becomes, and when I square the speed of light, I get 8.988 times 10 to the 16. All right, so then to finish it up, I'll divide both sides by the 8.998 times 10 to the 16. Remember that when you're dividing by numbers in scientific notation, you need to be sure to use that scientific notation button on your calculator, or you got to be sure to put the number in the denominator in the parentheses, otherwise you're going to get the wrong answer. All right, and so the mass that I get comes out to be 4.7 times 10 to the negative 9. And now your calculator might have had a bunch of zeros, but I've converted it from conventional notation into scientific notation. And then the units on the mass are always going to come out to be kilograms. And so that is our final answer. All right, and so when we stop and think about this, right, this is an extremely small number. 4.7 times 10 to the minus 9 kilograms is a crazy small number, right? So for chemical reactions, the change in mass associated with them is really small. And so this is why it took a long time to realize that mass wasn't necessarily conserved in chemical and nuclear reactions, because in chemical reactions, the change in mass is so small that the mass is effectively conserved. All right, let's do another example. Okay, so now we're told that the detonation of a W56 thermonuclear warhead will result in the loss in mass of 56 grams. And so we want to use this information to calculate the yield of this bomb, right? And the yield just means what is the energy given off. Now, one thing I wanted to point out before we work the problem is just to notice the differences in the masses involved, right? So here I've got 56 grams. That would be 0.056 kilograms. And so we compared that to the previous problem, right? For the chemical reaction, we had 10 to the minus 9 kilograms. And now we've got something that's like 10 to the minus 2 kilograms, right? So the differences in the changes in mass here are huge, right? For chemical reaction, like 56 grams, that's actually significant, right? So that's a significant change in mass for nuclear reactions. Whereas for chemical reactions, the change in mass is so small that it's basically insignificant. All right? But when we get down to doing this problem, it's just the opposite of what we did before. On the last example, They gave us the energy and wanted us to calculate the mass. In this case, they gave us the mass and they want us to calculate the energy. All right, now, I've told you what the mass is in kilograms, but let's go ahead and work the problem out fully. Right, remember I said on the last example, the energy needs to be joules and the mass needs to be kilograms. So I can't just plug the 56 into my equation, I've got to convert this to kilograms. So let's work out how I actually got this number. Right, and to get that, I use that 1 kilogram is equal to 10 to the third grams. So when I take my 56 grams, the 10 to the third grams will go on the bottom, the 1 kilogram will go on top, and so when I divide that out, I get 0.056 kilograms. All right, and this is what I'll plug in for the mass, right? We know the speed of light, and so then it's just solving for E. So we have E 0.056 times speed of light. Remember to square it. All right, so you could just punch all this into your calculator, but I'll work it out into 2 steps. First, I'll square the speed of light. And again, I get 8.988 times 10 to the 16. And so I'll multiply that by the 0.056. And so my energy comes out to be 5.0 times 10 to the 15. And the energy, right, the energy is always going to be joules. The mass is going to be kilograms. All right, and so then that's our answer to this problem. And I've got one kind of follow-up here that's just kind of for fun. Okay, so on the previous slide, we calculated that the yield of this thermonuclear warhead would be 5 times 10 to the 15 joules. Now, when we talk about the yield of nuclear weapons, we usually don't talk about it in terms of joules. We talk about it in terms of tons of TNT. So what we're going to do is we're going to convert the yield that we calculated in the previous problem in joules, and we're going to get that into tons of TNT. And so to do that, we're going to use that 1 ton of TNT is 4.184 gigajoules. And the giga prefix just means 10 to the 9th. So that means that 1 gigajoule is 10 to the 9th joules. Right? So all this is a unit conversion problem. So I've got the 2 conversion factors I need. So all I need to do is take my 5.0 times 10 to the 15th joules. So I want to get rid of joules. So I'll put the 10 to the positive 9 joules on the bottom is 1 gigajoule. Now I want to get rid of the gigajoules, so I'll put the 4.184 gigajoules on the bottom. The 1 ton of TNT will go on the top. Right, so remember, when these guys are in the bottom, that means I divide. So I'm going to take 5.0 times 10 to the 15, divide that by 10 to the 9th, then divide that result by 4.184. And we're going to get 1.2 times 10 to the 6 tons of TNT. Or we could go a step further. 10 to the 6 is a million, right? And the million prefix is mega, right? So we'd probably say that this is a 1.2 megaton of TNT nuclear warhead.